This lecture is about concavity and curve sketching. And I've had my first mess up. I held my pen down too long and my first page that I had photographed completely disappeared. So I had to redraw. So you should be looking at page 1 of your notes. I have drawn a red function right here, the sketch, and you should recognize that at that location right there I have a local maximum, and at this location right here I have a local minimum. We discussed that in the previous section. So let's discuss what concavity is. Hold your hand up in front of you and cup it like you're trying to hold water. And then turn it upside down like you are dumping the water out. When a graph is spilling water, we say that it is concave down from one x value to another x value. When the graph will hold water, we are saying that our graph is concave up from one x value to another. The location of the point where the graph changes from concave up to concave down is called an inflection point. From here to here, we're concave down, and then from here to here, we are concave up. So an inflection point is a vertical tangent. You recognize that from our discussion of differentiability, where the concavity changes, either from concave up to concave down, or from concave down to concave up. Let's look at the function y equals x cubed that we have graphed here in blue. So the blue is a function. What you see from this picture from your textbook has a whole bunch of tangent lines drawn to the curve, where the curve is concave down, and then where it is concave up. I have traced some of the tangent lines to that curve, and I want us to think about the steepness of those lines. In other words, their slopes. Please remember several of your understandings of a derivative, one of which is the slope of a tangent line to a curve. So if I am looking at the tangent lines as they are drawn on the curve from the left side of the curve to the right side of the curve, this first tangent line is very steep. As I progressively draw more tangent lines and get to this one, the slope of that tangent line is less steep. So my slopes, or my first derivatives, are decreasing. When my function is concave down, the slopes of the line tangent to the curves are decreasing. Now let's look at where my function is concave up. So that would happen on the right side of the y-axis. Look at this first tangent line. That does not have a very steep slope as compared to this tangent line, who does. So as I draw more and more and more tangents to this curve when it is concave up, what's happening is that their slopes, the first derivatives, the slopes of the tangent line to the curve, are increasing. So to summarize down here, how are the slopes of the lines that are tangent to the function changing when the function is concave down? Well, they are increasing. And when my function is concave up, the slopes are, I just did that backwards, sorry. These slopes are increasing, and these are decreasing. Now, I'm talking about slopes of tangent lines. So how would I find a change in a tangent line's slope? In other words, how would I find a change in a first derivative? That's a derivative mark right there. Well, to do that, I would take the second derivative. And the change in the first derivative is the second derivative. So to determine concavity, so when you are looking for concavity, you have to determine whether the second derivative is decreasing, which would be negative, or increasing, which would be positive. And I can test that by creating a second derivative number line. I think we are ready to go ahead and look at our first example. We are supposed to identify the coordinates of any local extrema. So these are first order critical points, which require me to find the first derivative, and the coordinates of any inflection points where my concavity is changing. And concavity I can determine by finding my second derivative. So I'm identifying coordinates, xy coordinates, of any local extrema and inflection points, and then I am graphing the function. Because remember, this section also discusses curve sketching in addition to concavity. So here's my function. We need to find first order critical points to find my local extrema. Remember, these are the points where the function is increasing or decreasing. Because if I'm going like this, I know I have a local max. And if I'm going like this on my number line, I know I have a local min. I'm then supposed to find second order critical points. Those simply mean the x values when I set the second derivative equal to 0. These are going to help me find my inflection points and any concavity. Concavity you have to find first to be able to find inflection points because you have to know your concavity is changing. So let's go ahead and take the first derivative of this function, which would give me 3 times a third, or, excuse me, let's erase that, x squared plus 2x minus 3. So that is my first derivative, x squared minus, plus 2x minus 3. We need to factor that. That would give me x plus 3 quantity times x minus 1 quantity. When I set that equal to 0, I get x equals negative 3 and x equals 1. Those are my first order critical points. So I am going to put those values on my number line. So I'm going to erase this to give myself some more room. So this is my first derivative number line. Here I'd have negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on. So these 2 points right here are my first order critical points. Again, refreshing your memory from what you did before, we need to do test points within these regions. I plug those into my first derivative in the factored form. When I do that, all I'm looking for is what kind of sign I get out. I'll get out a positive here, a negative here, and a positive here. Let's do one of these just to help you. Let's plug in the negative 4. So I'm plugging in negative 4 in both of these locations. Here I get a negative out. Here I get a negative out. A negative times a negative would be a positive. So this tells me that my function here is increasing, decreasing, and increasing. So I'm just reviewing for you guys. You weren't asked to find all this. I'm increasing from negative infinity to negative 3 and from 1 to infinity. And I am decreasing from negative 3 to 1. Let's see what kind of local extrema I have. I can tell here I have a local max, and here I have a local min. So I have a local max at x equals negative 3. If I want to find the y value, I take that value and I plug it into my original function, because I am finding information out about my original function. Here I have a local min whose x value is 1, and if I want to find the y value, I would do f of 1. Let's move on to our second derivative. Here was my first derivative, so my second derivative is 2x plus 2. Putting that in factored form, I get 2 times the quantity x plus 1. Setting that equal to 0, I get x is equal to negative 1. This is a second order critical point because it came from my second derivative. So let's put that on my number line. You guys are going to want to line up these number lines right on top of each other so that you can see what's happening, because you're going to need to learn to read them this way. So I have a second order critical point at negative 1. Please remember this is your second derivative number line. I'm going to do the same thing to test values that I do with my first derivative number line. I'm going to pick values in each region. I'm going to test them in my second derivative in the factored form. I'm not concerned with the number I get out, only with the sign. So when I plug a -2 in here, I'm going to get out a negative. When I plug in a 0, I'm going to get out a positive. These positive and negatives, these things tell me my concavity. I can tell that my function is concave down, because this is negative, from here to here, and that my function is concave up from -1 on. So if I were asked about my concavity, concave down from -infinity to -1, concave up from -1 to positive infinity. That means here at -1, where I'm changing from concave down to concave up, I have an inflection point at x equals -1. If I want to find the y value, I plug that -1 back into my original function, not a derivative, because all this information that I'm finding, local min, local max, inflection points, are about my original function. So again, what I would remind you to be able to graph easily, which we're going to do in a minute, is to keep your first derivative and second derivative number lines lined up. The book is giving us a procedure for graphing a function. You all know from college algebra how to find the domain of your function. You know how to find first and second derivatives from calculus. You can find your first order critical points from your first derivative and determine whether you're increasing or decreasing. You can determine your second order critical points from your second derivative, and they will tell you any points of inflection that you have and determine your concavity. If you have a rational function, identify any asymptotes. You remember how to do that from early in the semester. And then you are going to plot these key points. You're going to plot intercepts, you're going to plot local extrema, you're going to plot inflection points, and that's going to help you sketch your curve. So let's look at the function that I was just given, that I did all that work on so far. My function was 1/3 x cubed plus x squared minus 3x plus 5. Guys, what kind of function is that? You recognize it as a polynomial function, right? It has a domain then from positive to negative infinity. I can put in anything I want. I'm not going to have any holes or any asymptotes where my function is undefined. Let's real quickly see if we can find any intercepts. To find a y-intercept, you plug in 0 for every x. So when I do that and I do f of 0, I'm going to get out a 5. So I've got a y-intercept at 0, 5. To find an x-intercept, I plug in 0 for y, and when I do that, I would get 0 equals 1/3 x cubed plus x squared minus 3x plus 5, which I really don't want to do, because to find those x-intercepts would require all sorts of things like synthetic division and finding rational roots. But because it is a polynomial function, I can determine its end behavior very easily by looking at the dominant term, 1/3 x cubed. It has a exponent that's odd, and it has a positive leading coefficient Therefore, okay, you guys need to picture me up in front of the classroom, flapping my arms like a bird. You are exiting in quadrants 1 and 3. The first order critical points that we found a while ago, remember how we found x is equal to 3? Well, if I had done f of 3 in my original function, I would have gotten out of 14. Same here. When I had this critical point, let's see, our first one was a local max. When I plugged in, let's see, let's try this again. This should be a 1. When I plug in f of 1, I get out a 10/3, and please remember that this was the value of the local min. My second order critical points told me that x is equal to -1, and when I did f of -1, I get out 26/3. Please recall that this was an inflection point. So now let's actually go and graph some of these values. So recall I had a local max at -314. I had a local min at +1 10/3. By the way, do notice the scale on the y-axis versus the x-axis. I knew that my domain was all real numbers and that I was exiting in quadrants 1 and 3. I figured out that I had an inflection point at -1 26/3, which is a little bit more than 8. Now, I need you to go back and look at those number lines that you have. This is so much harder to do online than it is in person. But I need you to go back to that page where you're in your notes, where you have those two number lines, the first and second derivative number line drawn on top of each other. Now, the first one, remember, tells us where we are increasing. We are increasing to -3. So here we go. I'm increasing from where I am exiting, which was down here, to -3. All the while I am concave up. So my number line tells me that here I am increasing and I am concave up. And then I know that I am decreasing all the way until I get to an x value of 1. But at the same time, I am still concave down until I get to that inflection point. I messed up over there. So let me repeat. Look at the blue. My function was increasing and I was concave down until I got to -3. Look at the green. My function was decreasing from -3 to 1. Look at the purple. I am I am concave down from -3 to -1. All right, let's find another color here. So let's go to yellow. Please notice that from -1 on to positive infinity, I am now concave up. So the entire rest of the way, I am going to be concave up. However, I am decreasing from -3 to 1, and then from 1 to positive infinity, I am increasing. So hopefully, using a graph that had my points on it, but not the sketch, and just tracing over it, you can see how the information from my first and second derivative number lines helps me determine what the graph of a function actually looks like. All right, let's do another example. We're going to pick up the pace a little bit. Your directions ask you to identify the coordinates of any local extrema, the coordinates of any inflection points, and you can't read it because it's off the page. Whoops. But you are also being asked to graph the function. So let's do a little bit of the work here. My first derivative would give me x cubed minus 4x. When I factor out an x, I'd be left with x squared minus 4. When I factor my difference of squares, I would have x plus 2 quantity times x minus 2 quantity. Setting each one of these equal to 0, each factor, I would come up with first order critical points of 0, -2, and +2. I put those on my first derivative number line, -2, 0, and +2. I test those regions defined by my critical points. Those values, please remember you are putting them in the derivative, first derivative, into the factored form. So when I do that, I will get out negative, positive, negative, positive. That means my function is decreasing, increasing, decreasing, increasing. However, this time, remember, I'm not showing you everything. I'm only showing you what the question is asking us for. So, local extrema, I can find that I have here a local min at x equals 2. To find the value, I would do f of 2. I have a local max here, x equals 0, and f of 0 would give me the y value. Again, an additional local min. The x value is 2, and f of 2 would give me the y value. Let's do the second derivative work. I'm looking back up here. So I would have 3x squared minus 4. When I solve that for 0, 3x squared minus 4 equals 0. I come up with x equals plus or minus the square root of, let's try that again. Two over the square root of 3. That value is approximately negative and positive 1.15. So if I draw those values on my number line, critical points in my second derivative. Please recall that they tell you where your concavity is for your function. You're taking these test points, plugging them into the second derivative. There is not a factored form, so I'm going to plug it in here in the original one. When I plug those values in, let's just do one. When I plug in a -2, when I plug in a -2 and square it, I'm going to get out a positive times a positive is positive. It's larger than a 4, so this will be a positive value. I repeat the process, and so I know that my function is concave up in this region, down in this region, up in this region. I have chopped off some of my work. All right. On my next page, first thing I need to talk about is the domain. Please remember that your function was another polynomial function, so my domain was all real numbers. My polynomial function, because the lead coefficient was a dominant term, was 1/4 x to the 4, will exit in quadrants. We have a even exponent, and we have a positive lead coefficient, so I'll be exiting in quadrants 1 and 2. I can find my y-intercept very easily by plugging in 0 for x, and when I do that, I get out a 4. Again, I don't feel like finding the x-intercepts. Please remember that you had first order critical points of 2, 0 and -2, 0. I found the y values by plugging these two into my original function, not the derivative. My second order critical points, remember I got out a 2 over the square root of 3 that was positive and negative. When I plug those values into my original function, I get out 16/9, both positive. Here's the work. Now, I take that back. I did go back and find the x-intercepts. Your work is over here. I factored a 1/4 out of the left side of that equation. I'm looking at the trinomial that has 2 squares. Turns out this is a perfect square trinomial. Factors into this, and this, x squared minus 4 quantity squared. Both give me factors of x plus 2 times the quantity x minus 2. And because I have 2 of these, each of those are squared. Setting those equal to 0, I get out an x equals a -2 and an x equals a positive 2. So those are my x-intercepts. Let's look at the graph. Putting all that information on there, my local mins, my local max, my inflection points, the fact that I'm exiting in quadrants 1 and 2, I can easily figure out what my sketch needs to look like. Let's discuss what is called the second derivative test for local extrema. This test tells us that without having to look at the number line with the little pluses and negatives on it, we can tell from the concavity whether a local extrema will be a local min or a local max. So, for example, if I have a second derivative that is less than 0, so in other words this is negative, and I had somewhere within that region a first derivative that I could set equal to 0, then that critical point had to be a local maximum. If the second derivative within a region is positive, greater than 0, concave up, if I had a first derivative within that region set equal to 0, then it has to be a local minimum. This is simply telling you that if first derivatives and second derivatives are equal to 0, then you can't tell whether or not your function has a local max, a local min, or neither. For the next examples, the work is already there. Please recall all your completed notes are on Canvas as well as your blank notes. We're asked to do the same thing. Find the coordinates of any local extrema, local min, local maxes, and any inflection points, and to use that information to graph. So here is my function. Let's talk about it first. It's a polynomial function. Its domain is all real numbers. I can find the y-intercept by plugging in 0 for x, and I get out a 0, so there is a y-intercept. To find x-intercepts, I can set my function equal to 0. When I factor it, I get this work. I can set each one of my factors equal to 0 and solve, and I get the following x-intercepts. All right, this is pretty self-explanatory. To get out the y value, I plug 0 into my function, I get out a 0. Over here, I am setting this factor equal to 0, adding 5 to both sides, taking the square root of both sides, and I get what you see right here in this first line of work, that the x-intercepts are plus or minus the square root of 5/3. That's approximately plus or minus 1.3. When I plug those two values back into, nope, I'm not plugging those anywhere. Sorry about that. So here are my x-intercepts written as decimals. Please recall, if your factor only occurs an odd number of times, you're going to cross that x-intercept at that point. If a factor occurs an even number of times, you're going to touch. So that's why you see all these little crosses. I haven't done anything yet with derivatives. So I'm going to do the same work that I have done each time on the previous problems. I'm going to find first derivatives, set those critical points onto my number line. I am getting out critical points that are 0, -1, and 1. plugging in and picking and plugging in test values, plugging those into my factored form of my derivative, which would be right there, first derivative. Getting out little pluses and negatives, you can see those below the numbers. So my function is increasing, decreasing, decreasing, increasing because of the pluses and minuses. For those critical points, I went ahead and figured out what their y values are by plugging back into my original function. Let's go ahead and do the work for the second derivative. Here's my first derivative. Finding my second derivative, factoring out the common factor of 30x, setting each one of these factors equal to 0 and solving, I get x equals 0 and x equals plus or minus 1 over the square root of 2. That's approximately 0.707. So I found these by again plugging into my original function, plugging these values in. For the decimals, I use the original form, the non-decimal form. I am now going to take these second order critical points that I have underlined here, put them on my number line. You can see all three of those right there. I am going to divide my second derivative number line into intervals using those critical points. I am picking test values within those. I am plugging those back into the factored form of my second derivative. I'm getting out a negative, a positive, a negative, and a positive. So I know that I am concave down, up, down, and up based on those positive and negatives. From here, I can tell that I must have an inflection point right here because my concavity changed from down to up. I must have an inflection point right here because my concavity changed from up to down. I can tell I must have an inflection point right here because my concavity went from concave down to concave up. Take a minute and see if on a piece of graph paper or a spare blank graph that I have for you guys on Canvas that you can plot the y-intercept, the x-intercepts, the local min and local maxes, and your 3 inflection points. So pause your video and see if you can plot those points. You can see my x-intercepts. You can see my local max and local min, where they're located and what those values are. And you can see my inflection points. Because the dominant term of this original function was 3x to the 5th with an odd exponent in the dominant term and a positive leading coefficient, I know my polynomial function had to exit here and here. So far, all we've graphed are polynomial functions, which you learned enough to know how to graph those in pre-calc, except for finding the local mins and maxes and inflection points. Well, now we're going to graph something that you've never graphed before. Our example is a rational function. In the numerator we have x minus 4, and in the denominator we have x to the 2/3. Because this is a rational function, my domain is all real numbers except what's going to make the denominator 0, so x cannot be 0. To find the y-intercept, we plug in 0 for every x. That would give me an undefined denominator, so I do not have a y-intercept. You should recall from graphing rational functions that to find x-intercepts, all you need to focus on is the numerator of the rational function. When you set that equal to 0, you get out x is equal to 4. Because that factor, x minus 4 quantity, was to the first power, then I will cross at that x-intercept. Because I had x can't be 0, when I found my domain, I know that that is a vertical asymptote. Now, I need to point out something to you here that we haven't talked about before. You know that you need to look at the degree of the exponent in the denominator when you're trying to determine whether your sketch approaches the vertical asymptote from the same or opposite directions. Here is my exponent on my denominator that I'm looking at to determine same or different directions from the vertical asymptote. You don't care about the denominator of that. You only care about the numerator, which is even. And if you recall, that means we approach from the same direction. All right, let's erase some of this and talk about what kind of horizontal asymptote I have, if any. So, my horizontal asymptote. Please recall your horizontal asymptote rules. You're looking at the degree of the numerator and the degree of the denominator. The degree of the numerator is 1. The degree of the denominator is 2/3. Degree of the numerator is greater than the degree of the denominator. So therefore, I know that my asymptote is not going to be an oblique line because the degrees are not different by 1. They're different by a degree of, I can tell by looking, I don't know if you can, but of 1/3. So to figure this out, to find my asymptote, I am dividing my denominator into my numerator. I'm doing long division. X to the first divided by x to the 2/3 gives me x to the 1/3. Multiply x to the 1/3 times x to the 2/3 is x to the 3/3 because I add my exponents. Subtracting here gives me a 0. And please recall that since this will not go into, x to the 2/3 will not go into a -4 when I bring that down, then this is my asymptote. It's not linear. We have an asymptote that is a cube root. So, here's where you learned all that stuff in chapter 3 with your whole find the derivative, make it pretty, factor out the GCF, etc. So here is the work for the first derivative. I'm applying the quotient rule. Second thing I'm doing is making it pretty. My GCF is x to the 1/3. Factor it out. I've got a fraction, so I'm getting rid of it by multiplying by a form of 1. So now it looks better. Simplifying by distributing in the 2, and I end up with this derivative, which gives me this information when I set the numerator and the denominator equal to 0. I get out a -8 and I get out a 0. Remember, the numerator gives me possible local extrema. I got the -3 by plugging in -8 for my function. Remember, the denominator gives you vertical tangents, which in this case we already knew was a vertical asymptote at x equals 0. Repeat that really ugly process with the second derivative. So again, I am taking the derivative of the first derivative here. I am applying the quotient rule. I am working on making it pretty. I am factoring out the GCF. I am distributing that -5. I am simplifying everything. And when I do that, in factored form, here is my second derivative. So I'm going to set both the numerator and the denominator equal to 0, and figure out what my second order critical points are. I get out x is equal to -20 and x is equal to 0. The numerator gives me possible inflection points. To figure out what the y value is when x is -20, I evaluate my function at f of -20. I also get out x is 0, but we have already figured out up here that that is a vertical asymptote. So let's go look at our picture. All right. First of all, let me attempt to sketch in my asymptote here. So it is going to look something like that. I then plot, well, let me draw in my vertical asymptote next. Now let's plot some points. I have an inflection point, a local max. I have an x-intercept, and that's really it. So you are going back to your two number lines, your first derivative number line, your second derivative number line. Imagine you have these points with no curve sketched in. As you are looking at your number lines, you know you are increasing until you get to -8. So I am increasing from here to here. At the same time, I am concave up until I get to here. Concave up. And then I am concave down all the way to 0. Whoa. All right, concave down all the way to 0. Let's go back and notice that after I get to y is equal to x is equal to -8, I am decreasing until I get to 0. So here's 0. So now I am decreasing the rest of the way. After that, my first derivative number line tells me that from 0 to positive infinity I am increasing. And my second derivative number line tells me that I'm also concave down from 0 to positive infinity. So I have to be concave down and increasing the rest of the way. This graph that you see with all the colors on it is a very, I've drawn it out extremely well. On my notes down here at the bottom, I have an exaggeration of what this would look like to help you understand the concavity over here. All right, let's look at the next example. You are looking at another polynomial function. The process is the same. So I'm going to let you read through everything, and we are just going to come down here and look at this first derivative number line and this second derivative number line to help us graph. So I have a local max at 1, 1. I have a x-intercept at 0, 0, and 1 at 4/3, 0, which is like 1 1/3. I have an inflection point at approximately 0.6, 0.59. So I have an inflection point about right there. So when I attempt to sketch this, please notice that I am increasing and increasing. So from negative infinity to 0, I'm increasing. And at the same time, from negative infinity to 0, I am concave down. I continue increasing from 0 to 1, but from 0 to about 2/3, I'm concave up. So I'm going to exaggerate it like that. After 2/3, I'm concave down the rest of the way. So I need to be concave down and increasing, so like that. And then I am decreasing from 1 the rest of the way. But remember, I'm supposed to be concave down. So let's look over here at an exaggeration of that particular graph to help you see how that would be drawn a little bit better. All right, let's talk you through this last graph, and then I'll tell you the ways that I'm going to be able to test you on this material. Same directions we've been talking about. Here is my function. So I'm finding domain, y-intercept, x-intercept, as well as x-intercepts. Now let's talk about end behavior. You have two factors in your function. You have x to the first and x minus 5 quantity to the 1/3. If I were to distribute that x to the first n, my dominant term would end up being an x to the 4/3. Because that's a positive, and the numerator of that is even, my end behavior for this graph is that my original function will be exiting in quadrants 1 and 2. I do the same work that I have been doing for my first and my second derivatives, and I put that information on the first and the second derivative number lines, lining up the values underneath each other so that I can read how this graph is going to look to myself as I try to sketch it. Then I plot those points on the number line, follow my two number lines to determine increasing, decreasing, and concavity, and see if you can read your graphs to understand that I am concave down between positive 5 and 7.5, and that I am concave up between negative infinity and 5, and from positive 7.5 to infinity. So you can see from the yellow where my concave down would be. And then let me draw in my concave up. I think you get the general idea. So let's go on and talk about one of the ways that I can test here without giving you problems that are super long like the previous one. There's a worksheet on this material. If I were you, I would make sure that I do that. Look at what you're given. You're given some points. You're given some information about a first derivative and a second derivative. You are told here where your first derivative is less than 0, so negative. So this means where you are decreasing, and where your first derivative is greater than 0 or positive, so where you are increasing. Same thing here on the second derivative. You're being told what interval. Here's the interval. Your function is, second derivative is negative, so you know that you are concave down. And here you are told where you have a second derivative that's positive, so you know where you are concave up. So take a minute and see if you can draw that information on a number line. Did your number lines look like mine? On your first derivative number line, you are decreasing from negative infinity to 0 and from 2 to 0. And then you are increasing from 0 to 2. Your second derivative, you are concave down from 0 to 1. Let's try 1 to infinity. You are concave up from negative infinity to 1. So concave up here and down here. Now, go back and see if you can plot these points and successfully graph this information on your X and Y coordinate axes. So let's see if you did this question right. We are decreasing and concave up until I get to 0. So decreasing and concave up until I get to 0. Then from 0 to 2 we are increasing, but we are only concave up until we hit 1. At that point, while we're still increasing, we are concave down. I'm concave down the rest of the way, but now I am also decreasing again. So my sketch would look like that. Take a minute, see if you can plot these points. Draw first derivative number line and second derivative number line. Plot those points, and then we'll come back and sketch this curve together. So check out the number lines. Your first derivative number line is in yellow, your second derivative number line in green. I've plotted the points that we were given in blue. And now we are going to see if we can actually sketch this graph. We are increasing until we get to 0, and at that time we are concave down. So I'm increasing until I get to 0, and I am concave down. I'm still concave down until I get to 1, but now I'm decreasing. From 1 to 2, I'm decreasing, but now I'm concave up. From 2 to infinity, I'm increasing, but I'm only concave up until I get to 3, and then I'm concave down until I get to 5, and then I'm concave up after that point. So you should be able to identify an inflection point, an inflection point, an inflection point, and a local max and a local min. Please check out this next page that shows the chart about how the first and the second derivative actually affect the shape of your graph, which summarizes everything that we have talked about in this section.